Error analysis. Steady state error. The steady state error is the difference between the input and output of the system during steady state. For accuracy, the steady state error should be minimum. From the diagram, the input is R of S, the output is C of S, gain is G of S, and feedback is H of S. In this, error signal is E of S, and we know that E of S is nothing but R of S minus B of S. And if the feedback is negative, now I can write the equation E of S is equal to R of S minus B of S. And what is B of S? B of S is nothing but C of S multiplied by H of S. And what is C of S? C of S is nothing but I can write G of S and E of S. Now if I substitute these two equations in this, we get the equation as E of S is divided by R of S is equal to 1 divided by 1 plus G of S into H of S. And if I transfer R of S to the numerator, I get E of S is equal to R of S divided by 1 plus G of S into H of S. Now this is a very important equation to calculate steady state error. Now the steady state error of the system is obtained by final value theorem. That is, if t is a function of time with respect to infinity, then its Laplace transform is s will tend to 0 s into E of S. And if I substitute E of S as R of S divided by 1 plus G of S into H of S, I get the function as ESS is equal to limit s tends to 0 s into R of S divided by 1 plus G of S into H of S, where H of S is a unity feedback system. So ESS is nothing but limit s tends to 0 R of S divided by 1 plus G of S. Thus the steady state error depends on the input and the open loop transfer function. That is, the input is R of S and the open loop transfer function, that is G of S plus H of S. Now from the previous lecture, however, we already know what is a static position error constant, that is Kp, and what is Kv and what is Ka. Now Kp we got it from the position function, Kv it is the velocity function, and Ka is the acceleration function. And the test signal used for Kp is a step signal, for Kv it is a ramp signal, and for Ka it is parabolic signal. So if I want to find the value, how it behaves for a particular unit response, unit step function input, I just have to write the steady state error formula, that is ESS is equal to limit s tends to 0 s into 1 divided by 1 plus G of S H of S. Now here, what is this 1 by S? 1 by S is the input, that is R of S. So in the formula we had R of S divided by 1 plus G of S into H of S. If I substitute R of S as, since we are using unit step, R of S is 1 by S. If I further solve this, I get ESS is equal to 1 divided by 1 plus limit s tends to 0 G of S into H of S. So when s tends to 0, this whole function, I can call this as Kp. That is the static position error constant. So the Kp formula is this. That is Kp is equal to limit s tends to 0 G of S H of S. Now static velocity error constant. in this case, we know that ESS is equal to limit s tends to 0 s r of s divided by 1 plus g of s into h of s. And what is this r of s? We know that r of s is nothing but 1 by s square. 1 by s square because it is a ramp input we are using. The input that we are providing here is the ramp. So if I substitute this, I get ESS limit s tends to 0 1 by s square, that is the ramp input, divided by 1 plus g of s into h of s. So the final function I get is limit s tends to 0 s plus s into g of s h of s. If s tends to 0, this whole function will become 0. I can write this whole thing, that is limit s tends to 0 s g of s h of s as kv. So ESS is nothing but 1 divided by kV. So the static velocity error coefficient is given by kV limit s tends to 0 s g of s h of s. The next one is static acceleration error constant. We got this from parabolic test system. Now what is the input? Input is r of s divided is equal to 1 by s cube. This is the parabolic input. Now we have ESS, that is a steady state error formula is limit s tends to 0 s, and this is nothing but r of s, and we are using parabolic input 1 divided by 1 plus g of s into h of s. So again, if I multiply s cube to this function, I get, and one s and the other s gets cancelled. So what is left out is s square plus s square into g of s into h of s. Now I can write this part, that is s square g of s into h of s as ka. So this is the acceleration error constant. Now the steady state error for different type of system. Now if I consider type 0 system with unit step input, so the basic thing that you need to consider is the generalized equation for open loop transfer function, that is g of s into h of s. So it is nothing but k into 1 plus s into t1 1 plus s into t2 divided by s to the power of m 1 plus s into ta 1 plus s into tb. Now what is the formula we have? We know that for a unit step the input is r of s is nothing but 1 by s. Now if I want to find the value for error constant of kp, then the formula is limit s tends to 0 g of s into h of s, and g of s into h of s is nothing but k, that is kp. Again, it's nothing but kp. So I already know that for this steady state error for a unit step is ESS is equal to 1 divided by 1 plus kp. So for type 0 system, the static position error constant kp is finite. If you take type 0 system with unit ramp input, then kv is nothing but velocity error coefficient limit s tends to 0 g of s into h of s. And what is g of s into h of s is nothing but this generalized function of any system. Now since s tends to 0, 0 multiplied by the whole term, I get the answer as 0. So in steady state error, we know the formula for ramp, it is 1 by kv. So what is kv? kv is 0. So 1 by 0 is nothing but infinity. So ESS is infinity. Now for type 0 system with unit parabolic input, so what is the difference? Instead of kv we'll be using k, and in the formula instead of s we'll be multiplying with s square. So k is equal to limit s tends to 0 s square g of s into h of s. And what is g of s into h of s again? It is this whole function. Either you can substitute this function in the system, or you can substitute the basic function of error, that is r of s divided by 1 plus g of s h of s, and this is s into, since it is s, so I can write s square into r of s divided by 1 plus g of s into h of s. This is one way. The other way is you can directly substitute the value of s in this place. Then again it is, the answer we get is 0. So if I substitute 0 here, that is ka is 0, again it is 1 by 0, the value is infinity. So for type 0 system, the steady state error is infinite for ramp and parabolic inputs. Hence, the ramp and parabolic inputs are not acceptable. Similar to the previous, now we consider type 1 system with unit step input. So the formula for Kp is limit s tends to 0 g of s into h of s. Now g of s, if you put the value here, the Kp value will become infinity. So I get ES, steady state error for Kp. I know the formula as 1 divided by 1 plus Kp. So it is, the value is 0. Now for type 1 system with unit ramp input, we can write the formula as Kv is equal to limit s tends to 0 s into g of s into h of s. And this g of s, h of s is the generalized equation. Again, when I substitute the value there, the answer we get is k. So ESS is 1 divided by k, some finite constant. So k indicates a constant, a finite constant. The next is for the parabolic input. Again, the formula is Ka is equal to limit s tends to 0 s square g of s into h of s. Again, to this generalized equation, if I substitute s tends to 0, the equation I get for Ka is 0. So again, ES is 1 by Ka, 1 by 0 is infinity. So hence it is clear that for type 1 system, the step input and ramp input are acceptable because we are getting a constant value, and parabolic input is not acceptable because we are getting an infinite value for the parabolic input. So this is the summarized part of all the type system with different input. So for step input, for type 0 system, we get 1 divided by 1 plus k. Again, it's a finite value, it is acceptable. For type 1 system, it is 0, again 0, not acceptable. For unit ramp input, for type 0 system, we got infinite value. For type 1 system, it is 1 by k, and it is, for this we get 0. For unit parabolic input, we got infinity, but it is good value for, we got a constant value for type 2 system. As you can see, the diagonal values. Okay, so if I want to control the error in a system, and if it is type 0 system, I'll be going with unit step input. Now if I want to control the error in type 1 system, then I'll be going with the ramp input. Now if I want to control the error in type 2 system, then I'll be going with the parabolic input. Now for dynamic error coefficient, the steady state error coefficient gives the limited information. The error function is given by, we already know the error function, how we got this error function, that is E of s is equal to R of s divided by 1 plus G of s into H of s. For if there is a unity feedback, the H of s will become 1. There is a unity. So I get the function as 1 divided by 1 plus G of s. Now E of s divided by R of s is equal to 1 by k1 plus 1 by k2 into s plus 1 by k3 into s square plus, and it goes on. Let us assume that is E of s is equal to R of s divided by k1, s into R of s divided by k2, s square into R of s divided by k3. If I apply a Laplace inverse transform to this function, I get E of t is equal to 1 by k1 is the constant, and it is r of t. Here it is 1 by k2 r dot of t, that is d r of s divided by d r of t divided by dt, and it is 1 by k3, that is d square r of t divided by dt square. So in this case r of t, it indicates the unit step function with the value kp. Now in this case it indicates a ramp function which is the value of kv, that is the velocity, and in this case it indicates acceleration factor, that is k, with a parabolic input. The steady state error is given by ESS is equal to limit s tends to 0 s into E of s. If I keep on substituting in the initial part, I am taking step input. If I substitute the values, ESS is equal to limit s tends to 0, 1 by k1, 1 by s, because it's the step input. Again 1 by k2 into s, again 1 by s, again a step input, s square divided by k3, again a step input. So I get the final function ESS as 1 by k1. Similarly, for the other test signals, we can find the steady state error, and k1, k2, k3 is known as dynamic error coefficient. Now for example, instead of a unit step function, I can go with ramp function, a unit ramp function, that is 1 divided by s square, or I can go with 1 by parabolic, that is s cube parabolic function. I get a different steady state error functions or the output. Now we consider one example. Let us consider the open loop transfer function of a unity feedback system is given by g of s is equal to 50 divided by 1 plus 0.1 s plus 10. Understand this. For the formula we have is one is kp, kv and k. It is a product of g of s and h of s, and h of s should be always unity function. You should not have a feedback greater than a unity function. So in this case they are given the open loop transfer function of a unity feedback system. Already they have told you h of s is 1 and they are given a part of g of s. So I just need to substitute the values if I want to find the error coefficients. So kp is nothing but g of s into h of s. For kv I just need to multiply with an s because it's the velocity. For acceleration it is s square. I need to multiply with s square, and limit s tends to 0. So in the first case kp I got the value as 5. For kv I got 0. Ka I got 0. The block diagram of electronic pacemaker is shown in the figure. Determine the steady state error for the unit ramp input when k is equal to 400. Also determine the value of k for which the steady state error to a unity ramp will be 0.02. So as we know, the value of k is given in the forward path, and there is one more block 1 by s. So we have one block pacemaker and the other block is the heart, and this is a closed loop control system. So given that the value of k is 400, since it's a ramp unit, it is 1 by s square. Feedback is h of s. So g of s into h of s. For any steady state error, we take this formula. So it is nothing but k divided by s into s plus 20. Why? Because both of this block are in series. So we can product this. The steady state error is equal to ESS equals limit s tends to 0 s into r of s divided by 1 plus g of s into h of s, and this is the formula for steady state error. And in the given problem, the R of S is a ramp signal, so it is 1 by S square. And G of S into H of S, G of S is nothing but K divided by S into S plus 20, and H of S is multiplied by 1 because it is a unity feedback. The value we get, steady state error we get, is 0.05. So for value of K is equal to 500, the steady state error is 0.05. Now if I want to fix the steady state error to 0.02 or 2%, then what should be the value of K? So we'll use the same formula. In place of ESS we substitute the steady state error percentage is 0.02. So the value we get is K is equal to 1000. So if I want to reduce the error, I need to I can modify the value of K. Find the steady state error of the system shown in the figure when the reference input is R of t. That is, there are three inputs. One is delta of t, that is the impulse input. Next we have u of t, that is a step input. Next is the t into u of t, that means it's a ramp input. So if I use Laplace transform to this, I get 1 by s square. Now the given problem is this block, that is R of s. The error signal is E of s. The forward path is 5 divided by s plus 4, and the feedback path, which is a negative feedback path, that is 2 divided by s plus 1. So the steady state error formula, again it is as it is. ESS is equal to limit s tends to 0 s into E of s. So what is E of s? E of s is nothing but R of s divided by 1 plus G of s into H of s. So the first given signal is an impulse signal, that is delta of t. Since it's an impulse signal, the value will be equal to 1. So ESS is equal to limit s tends to 0 s into E of s. E of s is nothing but R of s, which is 1, divided by 1 plus G of s into H of s. So in this case, G of s is 5 divided by s plus 4, and H of s is 2 divided by s plus 1. The next signal, the answer we get for this is 0. The next signal is a unit step input, that is u of t. So ESS is equal to limit s tends to 0 s into s plus 4 s plus 1 divided by s plus 4 into s plus 1 plus 10 into 1 by s. Here 1 by s is for unit step, so answer we get is 4 divided by 14. The next signal is a unit ramp signal, that is t into u of t. So limit is s tends to 0, whatever the value we get, because it is 1 r of s divided by 1 plus g of s into h of s. So 1 by g of s into h of s is same for this condition as well as for this condition. The only change is r of s. So in this signal, r of s is a ramp signal, so it is 1 by s square. So the value we get is infinity. So what do you mean by this is, if the input changes, the steady state error values also changes. So in the first case, for an impulse signal, the error was 0. For step input, there was some constant, that is 4 by 14. For a ramp, the error became infinity. Now the next is find the steady state error of the system shown when the reference input R of t is delta t, that is impulse, step input, and a ramp input. So the given problem varies. So now we don't have any feedback values. It's a unit feedback path. Then we have a g of s as 10 divided by s into s plus 4. Again, the formula is same. There is no change in the formula. We are concentrating on the steady state error. So in the first case, it is the impulse input. So when we substitute 1 to it, and this is nothing but 1 divided by g of s into h of s. So since the impulse input, it is R of s is 1, so answer we get is 0. So if I use a step input, I'll be using 1 by s. The remaining whole thing is same as previous equation, because there is no such change, only the input R of s varies. Again, the value is 0. Now the last one is ramp input. So in the ramp input, it is 1 by s square. so I get some constant value. So again, if you compare this problem with the previous problem, since the control system module is different here, I get a different steady state error output. For the system shown in the figure, determine the system type number, static position error Kp, static velocity error constant Kv, ESS when R of t is U of t and T U of t, that is a unit step and a ramp, and this is the block diagram given. So this is G of S and this one is H of S. So to find the system type, we are only interested in open loop transfer function. So by just seeing the open loop transfer function, we can say the system type. So G of S into H of S, I can easily write 20 divided by S into S plus 5 plus S plus 3. So if I equate the denominator, that is a characteristic equation, to 0, then I can, there are S is equal to 0, that is S1, S2 is equal to minus 5, and S3 is equal to minus 3. So if I write the S domain plane, or I can say S plane, then there is one pole at 0, that is S1 is equal to 0. There is another pole that is minus 3, and there is another pole which is minus 5. And this is nothing but sigma, or the real axis, and y axis is nothing but imaginary axis. Okay. So static position error. So if the formula is same, Kp is equal to limit s tends to 0, g of s, h of s. We already know what is g of s into h of s. So if I substitute the values, I get the answer as infinity. In the next case, Kv, the formula is, I just need to multiply s to it to get Kv. So limit s tends to 0, s g of s into h of s. So limit 50 into s. So this and this s get cancelled, and there is a mistake here. This is not 5, this is not 5, it is actually 3. So s is 0 0, so it is 20 divided by 5 into 3, that is 50, 20 by 50. Now the last one is, we need to find the steady state error for a unit step input and a ramp input. So for unit step, I know the formula is 1 divided by 1 plus kp. For ramp it is 1 by kV. So the answer I get is 0, and the other answer I get is 15 by 20.